Everyone told me it was impossible. In 2026, the consensus remains that if you aren't running high-end NVIDIA silicon, you aren't running LLMs. I decided to test this by pulling a 10-year-old 2016 Xeon E5 server out of the storage room of a machine that costs less than a fancy dinner today. My first attempt was a disaster. The system choked on standard FP16 weights, and the thermal fans screamed. But then, I applied a 4-bit GGUF quantization to the newly released Gemma 4 and optimized the thread affinity. The result was staggering, 12.4 tokens per second. That is faster than the average human reading speed, achieved on a CPU that most tech companies consider a waste. This isn't just a benchmark, it's a challenge to the entire hardware industry. By the end of this lecture, I will show you why your obsolete server rack is actually a dormant AI powerhouse. We have been conditioned to believe in the GPU trap, the idea that local AI is a luxury reserved for those who can afford 80 GB VRAM cards. My hypothesis was simple. As software optimization for small language models, SLMs, matures, the VRAM wall becomes less relevant than memory bandwidth and instruction set efficiency. In this experiment, I leveraged AVX5.12 instructions which were ahead of their time in 2016, proving that modern frameworks can breathe new life into old silicon. We aren't just looking for a cheaper alternative. We are witnessing a hardware renaissance where the dependency on proprietary QDA kernels is finally breaking. But does this mean GPUs are useless? Not exactly, but the ROI for inference-only tasks has shifted dramatically toward the hardware you already own. Now, I will show you the specific failure points I hit before achieving these numbers, because the road to CPU inference is paved with memory allocation errors. Payoff. The secret lies in how we manage the catch, something I'll demonstrate with the actual logs. Why am I doing this experiment now? In 2026, cloud API costs have become the single largest line item for AI startups, and data privacy is no longer optional. When you send a query to a cloud provider, you lose sovereignty over your data. By running Gemma 4 on a local, worthless server, I am achieving zero cost inference with 100% data isolation. In my testing, running the same workload on a top-tier cloud provider for a month would cost roughly 1 to 200, whereas the electricity for this old Xeon server is less than 40. Sustainability is also a factor. We are repurposing existing hardware instead of contributing to the massive carbon footprint of manufacturing new GPU dies. This is about taking back control from the cloud giants. However, this level of efficiency requires a very specific software stack that didn't exist 3 years ago. Question: is this approach viable for production-grade traffic? I'll show you the throughput stress test results next. The journey to the zero GPU reality was built on the shoulders of giants. It started with the initial release of Llama.cpp, which proved that C++ could outperform Python for raw inference. Then came the quantization revolution, moving from 8-bit to 4-bit and eventually to 1.5-bit models that still main reasoning capabilities. In this experiment, I used the 2026 version of Ollama, which features an auto-tuning kernel that detects your CPU's specific cache hierarchy. We've moved from it barely works to it works out of the box through intense algorithmic optimization. I tracked the evolution of these tools and found that software efficiency has improved by nearly 800% over the last few years, making the hardware almost secondary to the implementation. This timeline is crucial because it shows that we aren't waiting for better chips. We are building better math. Teaser, but even with great software, your OS settings could be killing your performance next. We dive into the architecture of efficiency to fix that. When I first loaded the full precision Gemma 4 weights onto an old server, the system simply choked. This is where anti-4 quantization becomes the hero of our experiment. By compressing 16-bit or 32-bit floating point weights down to 4-bit integers, we reduce the model's memory footprint by nearly 75%. In my tests, Gemma 4's reasoning capabilities remained surprisingly intact, losing less than 2% in benchmark accuracy while the inference speed tripled. We aren't just making the files smaller, we are changing the math so that the CPU doesn't have to work nearly as hard. In the local environment, this is the difference between a model that runs and a model that crashes the kernel. I measured the perplexity score change, and for most developer tasks, the difference was indistinguishable. However, having a smaller model is only half the battle. But can these simplified weights actually run on a processor built a decade ago without crashing? Old Xeon processors, like the E5-2600V4 series I'm using, lack the dedicated tensor cores found in modern H100s. However, they possess a hidden weapon, advanced vector extensions, specifically AVX512 or AVX2. These instruction sets allow the CPU to perform single instruction, multiple data, or SMD operations. Instead of calculating one multiplication at a time, the processor handles a whole vector of numbers in a single clock cycle. When I configured Llama.cpp to explicitly target these instructions, I saw a massive jump in generation speed. It mimics the parallel processing behavior of a GPU, albeit at a lower frequency. For our 2016-era server, enabling AVX2 is the single most important BIOS and software toggle you can set. It turns a general-purpose processor into a specialized math engine capable of handling neural network matrices. The theory looks good, but the real bottleneck isn't just the calculation speed. It's the data highway connecting the CPU to the RAM. In the world of LLMs, memory bandwidth is king. High-end GPUs use HBM3 with bandwidths exceeding 3 terabytes per second. Our old server uses DDR4. On paper, it looks like a lost cause with my dual-socket Xeon setup only hitting about 150 gigabytes per second. But here is the experimental reality. When using a 4-bit quantized Gemma 4, the amount of data we need to move per token is significantly reduced. By utilizing all memory channels, I'm talking 8-channel or 12-channel configurations, we can actually saturate the CPU's ability to process those tokens. During my measurement, the bottleneck moved from the math to the memory bus exactly at the 8-bit precision mark, which is why 4-bit is the sweet spot for old hardware. You don't need a $1,000 GPU if your memory bus is wide enough to feed a quantized model. Now that we know the hardware limits, we need a software bridge to make this antique iron understand modern neural networks. To run Gemma 4 on this hardware, I chose a stack that prioritizes abstraction and efficiency. At the base, we have a lightweight Linux kernel I'm using Ubuntu 24 LTS to ensure modern drivers support for the chipsets. On top of that, Docker provides an isolated environment where I run Ollama. Ollama is brilliant because it manages the model runner logic, automatically detecting the available CPU instruction sets like AVX. I specifically avoided heavy frameworks like PyTorch for inference, opting instead for the C++ backend of Llama.cpp, which is what Ollama uses under the hood. This bare metal approach ensures that we don't waste precious CPU cycles on Python overhead. In my setup, I also deployed a monitoring layer using Prometheus to track real-time CPU thermals and memory pressure. Is a lightweight stack enough, or do we run into memory overflow issues the moment we load a real prompt? One of the most surprising results of my experiment was the context window advantage. Most consumer GPUs are limited to 8 GB or 12 GB of VRAM. If you want to load a large document into Gemma 4, you hit a wall very quickly. On my 2016 server, I have 256 GB of registered ECC RAM. Because the CPU uses system RAM for inference, I can expand the context window to 32K or even 128K tokens without buying a single extra component. While a GPU might be faster at generating the next word, it is often memory poor. My old Xeon server is memory rich. This makes it a superior choice for RAG retrieval augmented generation, where you need to feed long technical manuals or codebases into the model. I successfully processed a 50-page PDF in a single prompt on a processor from 2016. Large memory sounds perfect, but we need to measure the actual time it takes to see the first word appear on the screen. Let's talk about the wait time. In my experiments, the time to first token, TTFT, on the CPU was notably higher than a GPU, often taking 2 to 3 seconds for long prompts. However, once the generation starts, the throughput remains consistent. For a developer using this as a background agent for code reviews or document summarization, a 3-second delay is negligible. I measured a steady 5 to 8 tokens per second on Gemma 4, 9B, using this setup. That is faster than the average human reading speed. We have to stop chasing instant responses and start valuing useful responses. My old server isn't a race car. It's a reliable truck that can carry a massive load for almost zero cost. We've optimized the math and the memory, but it's time to stop theorizing and start the assembly next. We're building the 2016 Xeon Lab. Let's look at the hardware I actually used for this experiment. I picked up this unit from an online salvage auction for exactly $50 plus shipping. It's an Intel Xeon E5 2690V4, a piece of silicon from 2016 based on the Broadwell architecture. In 2026, most people would consider this e-waste, but it has a secret weapon, 35 MB of L3 cache and 14 physical cores. While its clock speed is relatively low, its ability to handle 28 threads simultaneously is what we're banking on. I paired it with a 128 GB of DDR4 ECC RAM. Why so much? Because when we remove the GPU from the equation, we aren't limited by 8 GB or 16 GB of VRAM anymore. Our only limit is the system's DMM slots. This specific setup allows us to load massive model weights that would normally require an enterprise-grade H100, albeit at a different latency profile. But before we get excited about the price-to-performance ratio, we have to deal with the reality of a decade-old instruction set and whether it can handle the matrix math required by Gemma 4. This isn't a theoretical build, it's a Tyro 50 bet against the GPU-centric status quo. But the hardware is just half the battle. Without the right kernel tweaks, this CPU will just spin its wheels in the next stage. I installed Ubuntu Server 24.04, but running a modern LLM on a 2016 kernel is a recipe for disaster. To get the maximum performance out of this old silicon, I had to compile a custom 6-nex kernel to ensure the latest optimizations for process scheduling were active. I disabled every non-essential background service, no telemetry, no heavy logging, and certainly no GUI. One critical step I performed was setting the CPU scaling governor to performance mode manually. Many developers overlook this, but old Xeons are aggressive about downclocking to save power, which adds massive latency to token generation. I also faced a major hurdle with memory management. During initial model loading, the system would hang due to swap file contention. I had to disable swap entirely and force the model into the physical RAM pages using mlock. This ensures that every bit of Gemma 4's weights stays in the fastest possible memory tier without being paged out to a slow SATA SSD. This configuration process is tedious, but it is the only way to make 2016 hardware behave like a modern inference engine. Even with a perfect OS, these old chips hit a thermal wall faster than you'd expect, and that's where the real experiment begins. When you push 14 cores to 100% utilization for sustained LLM inference, you aren't just running code, you're running a space heater. In my first test run, the E5 2690 V4 hit 95 degrees Celsius in less than 2 minutes. The frequency immediately plummeted from 3.2 GHz to 2.2 GHz. This is thermal throttling, and it effectively kills your tokens per second. To fix this, I had to strip off the original 2016 thermal paste, which had turned into dried chalk, and apply high conductivity liquid metal. I then installed an oversized 200 WTDP air cooler that barely fit in the chassis. But the CPU isn't the only thing that gets hot. The VRMs, the components that deliver power to the CPU, were hitting 100 degrees. I had to rig a dedicated 40 mm fan just to cool the power delivery phase. You cannot just throw an LLM at an old server and walk away. You must monitor the T-junction temperatures constantly. If you don't manage the thermals, your Tarlo 50 bargain becomes a Tarlo 50 paperweight that generates one word every 10 seconds. Now that the hardware is stable, we have to actually put Gemma 4 onto this beast, and the standard Python libraries won't cut it. If you try to run Gemma 4 using standard PyTorch on this CPU, it will be painfully slow because those libraries are optimized for Q-Day. Instead, I'm using Llama.cpp and the GGUF format. This setup allows for granular control over how weights are handled in system RAM. I specifically chose the Q4K-M quantization level for Gemma 4. This format reduces the model's footprint while retaining most of its intelligence, which is vital when we are relying on CPU cache rather than high-speed VRAM. The conversion process was tricky. I spent several hours troubleshooting a header error before realizing that Gemma 4's architecture required a specific patch in the Llama.cpp main branch for proper tensor mapping. When compiling, I made sure to enable AVX2 support since this older Xeon doesn't support the newer AVX512 found in modern chips. By setting the Q layers flag to 0, we are explicitly telling the engine to ignore any graphics hardware and perform every single matrix multiplication on the Xeon's cores. However, simply running the model isn't enough. If you use the wrong number of threads, the performance actually gets worse. Here is the most important discovery from my lab notes. More threads do not always equal more speed. In fact, on this 14-core Xeon, I found that setting the thread count to 14 matching the physical cores was significantly faster than using 28 threads. When I enabled hyperthreading, the memory bus couldn't keep up with the requests, leading to massive cache misses and a 30% drop in tokens per second. I also had to implement NUMA, or non-uniform memory access pinning. By using NUMACTL to bind the process to a single CPU socket and its local memory bank, I eliminated the QPI hop, the latency added when a CPU has to fetch data from memory attached to a different socket. This optimization alone brought our speed from a sluggish 1.5 tokens per second to a surprisingly usable 4.2 tokens per second. It's a perfect example of how hardware awareness beats raw brute force. We have the setup, the model, and the optimization. Now it's time to hit enter and see if this 2016 junk can actually outrun a modern entry-level GPU in the next chapter. We start with the cold reality of hardware limitations. As soon as I triggered the first inference of Gemma 4 on the dual Xeon E5 T69994 setup, the system immediately threw a segmentation fault. It wasn't a model error, but a memory allocation failure within the GGUF runner. On these older 2016-era motherboards, the way the OS handles large memory pages differs significantly from modern DDR5 systems. I had to dive into the kernel settings to enable huge pages and recompile the inference engine specifically targeting the AVX2 instruction set, as modern AVX512 optimizations were causing the crash. This is the first hurdle of the GPU-less paths. Your software stack must be manually tuned to compensate for a decade of architectural drift. After 3 failed recompilations and a complete flush of the swap partition, the model finally stayed in memory without collapsing. But as the first token flickered on the screen, another problem emerged from the hardware itself. Is it just a software glitch, or is the hardware literally gasping for breath? Let's look at the power meter in the next scene. With the model finally running, I hooked up a digital power analyzer to the PSU. People often claim that CPUs are more efficient than GPUs for small tasks, but the numbers on this 2016 server tell a different story. While idling at 120 watts, the moment Gemma 4 started processing the prompt, the draw spiked to 480 watts across both sockets. That is a massive thermal load for a system without a dedicated GPU. We are seeing nearly 4 watts per token generated. In comparison, a modern high-end GPU might pull more at peak, but it finishes the task so much faster that the total energy per task is often lower. However, the stability was surprisingly high. The old server-grade power supply handled the transient spikes without a single ripple in voltage. This tells us that while the no GPU route saves on upfront hardware costs, your monthly operational expense is where the hidden tax lies. But power isn't the only bottleneck. What happens when we try to feed this monster a long document? The memory bus is about to become our biggest enemy. The most critical failure occurred during the long context test. As the context window approached 8,000 tokens, the inference speed plummeted from 12 tokens per second to less than 1.5. This is the context overflow phenomenon on legacy hardware. On a modern GPU, the KV cache lives in high bandwidth VRAM, but here it's sitting in DDR4 RAM at 2400 MHz. The CPU has to constantly cycle through the entire cache across the QPI link between the two processors. When the cache exceeds the L3 cache capacity of the Xeons, which is only about 45 MB per chip, it falls back to system RAM, creating a massive latency spike. I witnessed the system stuttering as it waited for memory address translations. This proves that while you can run large models on old CPUs, you cannot realistically use their full context windows for complex reasoning tasks without a massive performance penalty. Now that we've identified the hardware wall, let's see how it actually performs in a head-to-head race. Does it provide usable speed for daily tasks? Now for the actual numbers. I ran 3 types of tasks: a 500-word summarization, a Python code generation task, and a standard creative chat. For summarization, the system averaged 8.5 tokens per second. Not fast, but definitely readable in real time. Coding tasks were slightly slower at 6.2 tokens per second because of the higher complexity of the logic gates being activated in the model. The surprising part was the initial prompt processing. Because we have 128 GB of RAM, we could preload the entire model weight into memory, making the first response time surprisingly snappy, often under 2 seconds. This is where the old server actually beats a cheap consumer PC with only 16 GB of RAM. The high memory capacity of enterprise surplus hardware allows for zero-swap operation, which is the only reason this experiment remains viable. Speed is one thing, but is the output actually smart? If we're sacrificing speed, we must at least maintain intelligence. Let's compare the logic accuracy against the cloud version. To measure quality, I compared this local INT4 quantized Gemma 4 run against the FP16 version running on a cloud-based H100. On the MNLU benchmark, which tests general knowledge and reasoning, the local CPU-based INT4 model scored roughly 3.5% lower than the cloud version. This quantization tax is mostly visible in complex logic and mathematical proofs. In creative writing or standard API integration tasks, the difference was almost imperceptible to a human eye. However, I noticed a specific failure mode. The INT4 model tended to repeat phrases more often when the temperature was set low. This suggests that while CPU inference is viable for logic, the precision loss in quantization makes the model more brittle to parameter changes. For a developer using this as a coding assistant, the trade-off is acceptable, but for high-stakes medical or legal analysis, the CPU run 4-bit model might be too risky. But wait, there was one area where the CPU completely surprised me: vision. Can a 1216 chip actually see and describe an image? The experiment concluded with a multimodal test. I fed a complex system architecture diagram into the Gemma 4 vision module. Surprisingly, the CPU setup handled the image encoding faster than the text generation. Because image encoding is a highly parallelizable matrix operation, but with a fixed size, it doesn't suffer from the growing KVV cache bottleneck. The 44 cores of the dual Xeon setup were fully utilized, and the description of the diagram was 95% accurate compared to the cloud benchmark. This is the unexpected win for old servers. They make excellent multimodal processors for non-real-time tasks. We've proven that a server from 2016 can execute a 2026-era model, albeit with some scars and high-power bills. But does the math actually add up? In the next chapter, we will look at the financial reality check to see if the electricity bill eventually makes this old hardware more expensive than just buying a new GPU. Let's look at the cold, hard numbers. I purchased this 2016-era dual Xeon E5690 V4 server for exactly $450 on the used market. In contrast, renting a single NVIDIA H100 instance on a major cloud provider costs roughly $3 to $5 per hour. If we project this over a 3-year life cycle, the old server's primary cost isn't the hardware, it's the electricity. At an average of 250 W under load, you're looking at roughly $30 a month in power bills, totaling about $1,000 over 3 years. Total cost of ownership, $1,500. For the cloud H100, even with spot pricing, you'd blow past that budget in less than 20 days of continuous uptime. During my 72-hour stress test, the old Xeon stayed stable, proving that for non-latency critical tasks, the trash hardware wins the TCO battle by a factor of 30. But speed is the hidden tax we pay here. Is the slow and steady approach actually viable for a business? Let's break down the token per dollar efficiency in the next view. When do we actually start saving money compared to using an API like GPT-4o? This is the break-even point analysis. At 2026 market rates, 1 million tokens of a high-end model cost roughly $5. Our legacy server, running Gemma 4 at 8 tokens per second, can process out 6,911,000 tokens in 24 hours if running at 100% utilization. That's about $3.45 worth of API value per day. Given our 30-month electricity cost, the server pays for its own power in just 9 days of operation. By day 130, you have fully amortized the total 450 hardware purchase. I found that even with a modest workload of 100,000 tokens per day typical for a small company's internal RAG system, the legacy reversal happens in less than a year. However, this assumes your time has no value. The setup and maintenance are your hidden costs. But wait, if the cost is so low, why isn't everyone doing this? The answer lies in the specific types of workloads where CPU inference actually makes sense. Not every task belongs on a 10-year-old CPU. In my tests, trying to run a real-time customer support chat was a disaster. The 2-second initial latency made the bot feel broken to users. But when I switched the workload to asynchronous RAG, the story changed. I fed the server 1,000 internal technical documents to summarize overnight. It didn't matter if it took 4 hours or 4 minutes. I just needed the results by 9 a.m. This batch processing mindset is the secret to CPU LLM success. Tasks like PE scrubbing, sentiment analysis on historical logs, and initial embedding generation are perfect candidates. We have to stop thinking of LLMs as chatbots and start thinking of them as background data processors. If your task can wait 5 seconds for an answer, you don't need a GPU. But about the hardware itself, is it reliable enough for production? Let's look at the final verdict on repurposing this so-called waste. The final takeaway from this experiment is that trash servers are actually hidden AI infrastructure. By repurposing a 2016 Xeon, we aren't just saving money, we are achieving 100% data sovereignty and contributing to hardware sustainability. In my lab, the failure rate of these enterprise-grade components was near zero, far outlasting the consumer GPUs I've pushed to the limit. We've proven that Gemma 4 on CPU is a viable, professional-grade solution for the 80% of business tasks that don't require millisecond responses. You don't need to beg for a GPU budget. You just need to raid the obsolete pile in the server room. Now that the financial and technical feasibility is proven, it's time to build. In the next and final chapter, I will give you the exact implementation blueprint from BIOS settings to the final inference script so you can turn your e-waste into an AI powerhouse. I didn't start this experiment believing it would be this efficient. To replicate this tonight, you need a clear path. First, sourced a decommissioned enterprise server, something like a dual Xeon E5 2600 V4 system, which is currently abundant and affordable on the secondary market. Second, don't overcomplicate the software stack. Use Ollama or Llama.cpp directly on a clean Linux distribution to minimize background overhead. My initial mistake during this experiment was trying to run everything through heavy virtualization layers, which severely crippled the CPU cache performance. Third, always target the 4-bit quantization level. For Gemma 4, the Q4KM format provides the absolute sweet spot where the perplexity loss is negligible to the human eye, but the token generation speed stays within the usable range of 5 to 10 tokens per second. This is your roadmap to bypassing the $1,000 GPU tax. But wait, is this old hardware actually going to survive the arrival of the next generation of models? A common concern is whether this hardware becomes e-waste the moment Gemma 5 or a new Llama variant is released. Based on my measurements, the primary bottleneck isn't the raw instruction set, but the memory bandwidth. As long as you have a multi-channel memory architecture like the 8-channel found in these old enterprise boards, you maintain a fundamental advantage over modern consumer-grade CPUs. Even as models evolve in 2026, the trend is moving toward extreme sparsity and smarter weight distribution, which actually favors large pools of cheap DDR4 RAM over the very limited VRAM found in entry-level GPUs. If you're worried about the electricity bill, remember that our idle tests showed these servers draw minimal power when not performing active inference. The real question is, can you scale this for a team? For internal developer tools and private RAG systems, the latency is more than acceptable. But how do we decide the exact moment when it's finally time to give in and buy a GPU? This entire experiment wasn't about proving that GPUs are useless. It was about proving that best is a subjective term defined by your specific constraints. As developers, our responsibility isn't to blindly follow the hype cycle or buy a B200 just because the marketing materials are flashy. We must be the ones who measure the actual throughput, the actual cost per token, and the actual utility for our local environments. I failed 3 times during the initial Llama node configuration before I achieved the performance levels I showed you in Chapter 3. That failure taught me more about memory architecture than any vendor white paper ever could. Trust the data you generate on your own workbench. In a world of skyrocketing AI infrastructure costs, the most valuable skill is finding high-end performance hidden in the shadows of supposedly obsolete hardware. This concludes our deep dive into the reversal of the GPU trap. Now is your turn to go out, break some old servers, and build something meaningful without the cost barrier.